Hi everyone, we are back and we are going to now talk about discrete Fourier transforms, and we are going to calculate discrete Fourier transforms, look at frequency spectrums, determine dominant frequency, maximum frequency, and fundamental frequency, as well as kind of this concept of signal aliasing. So what we have to do is we're going to use our same equations that we did last time to calculate our continuous Fourier transform harmonics. The magnitude of those harmonics, but now all we're going to do is we're going to discretize our system. So instead of y of t, we're just going to plug in the value of y r at specific delta t's, where r is just going to vary from 1 to n. So it's just an integer counter, integer counter, and it just varies from there, and you just plug in the value of y at that specific delta t. So like y of 1 delta t. What is that value? It could be 5. And then y of 2 delta t, whatever it is in your system. And it could be 6 or minus 1, whatever. We already know we can convert t to n delta t. And other than that, we can also look at, instead of doing, again, an integral, what we're going to do is just take a summation. So we're going to, and instead of this dt, we're going to substitute a delta t, and then we're going to sum from r from 1 minus 1 to infinity, or base r from 1 to n. So that's essentially what we're working with here. So we can make those substitutions. When we do that, we can make another reduction, and then we get to kind of the final expression that we're going to be working with, and we get this final expression here. Now, it's important to note, we will do our summation from r equals 1 to n, but our number of harmonics goes to n over 2. Now, why is this? This is because this is our Nyquist frequency. So if you look at your Nyquist frequency, your f of s is equal to 1 over delta t. So, and you can rewrite that essentially. You can see this here, and it's going to stop at n over 2. So you can go ahead and see that this will be, so that is our f Nyquist, and we can rewrite that. So if you have, actually we had it up here. Excuse me for backtracking here. I'm just going to go over here. So if we have our period t is n over f sub s, and you can essentially rewrite that and find essentially your Nyquist frequency as well. So we're going to go only to n over 2 because that will be basically that Nyquist frequency. Basically, we can only sample, So if you remember, f of s has to be greater than twice our Nyquist frequency, f Nyquist. So basically, at that limit of where we can actually determine and find out frequencies, it has to be f of s over 2 or n over 2 harmonics. So there you go. That's pretty much it. Our delta f is just going to be 1 over t, 1 over n delta t, f of s over n, or again, we can make that substitution here and basically make it 2 f Nyquist over n. Again, that's like the limit essentially that you're hitting there. So your largest frequency will be this, n over 2. So we can do that in kind of this form here, which will be your f Nyquist over n. That cancels. So exactly, you can kind of get that delta f is equal to f Nyquist over 2, which is going to be effectively what we've been seeing essentially here. But yeah. So remember, again, that's really an important aspect of it. We're only going to n over 2 here, and that will be essentially that Nyquist frequency. So otherwise, you're just going to get a mirror image, and you can really visualize that quite well on those graphs. So make sure, again, we're leveraging this relationship. This is very, 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 very important, but it limits essentially the frequencies that we can actually see in our signal. Fantastic. So let's actually look at how this will work. So let's say I have a data set where I have my data, I have some time values, and then I can see essentially here, I'm going to zoom out just a little bit. This is my discrete data set. So I can start to define some critical parameters. So my big N, which will be the length of my data set. So we can actually even say big N equals here. I can also say that my, TDAT, if I look at the differences here, my differences are going to be this. So they're all the same. So I can just pick out one. So this would be my del t. My f of s equals 1 over del t. My delta f equals 1 over big N times del t. Actually, I should define the period. I'm just going to say capital T equals big N times del t. I know that my delta f is equal 1 over t. And then now we've defined essentially a lot of our key parameters here. So I can run this code to find, and actually you see here, and this is just to kind of show you what's happening. I can calculate my harmonics. I've already got my period, a sub n. You see it's just flipped. So it's just a mirror image. So we don't want it to length of data. We want it divided by 2. Remember 0 to n over 2 to that Nyquist frequency. And then now we can see no more mirror images. So when we plot, we want to plot, again, as integers of delta f. You can start, and actually you can see here, length of an. Now, there's a little bit of a typo here because that n is our 0th order harmonic. So really, yeah, I goes from 0 to here. Yeah, so no, actually, we're completely fine. And this will be our frequency spectrum. So we can see the dominant frequency is actually right here at 333 hertz. Now, this is the point where we're going to talk about a concept that's known as signal aliasing. And actually, we can confirm some parameters as well. We also said that our f Nyquist has to be, or our f of s has to be greater than fs divided by 2. That's going to be 1,000. That's our Nyquist frequency here. We don't see any mirror imaging, so we know that this is only to the maximum frequency, or it should be only to the maximum frequency. We also can see our delta f, so you can work inverse from looking at these plots as well to make sure that we have indeed what we want to have. Now, we have all these good things. We ran through our analysis. Here's our frequency spectrum, but this is actually one of the key problems here, or one of the key potential issues that can arise. For example, 333 hertz. What if I have a signal that's at 250? What if there's a really dominant signal here that I'm missing? Because I'm only measuring this frequency. Well, that is going to leak here and here. So depending on how, depending on the resolution of the frequencies that you need to measure, you really have to control delta f and make that as small as possible to hit. So for example, if I know in my signal, I have signals at 5.6, 3.1, 10, 100, and 50, I need to make sure, if I want to hit all these signals, I need to have a delta f of at least 0.1, right? Because then that'll allow me to hit all these different signals. So signal aliasing is critical it's critical to control your delta f and thus your n delta t, because that is delta f. You need to control this to make sure that you have enough resolution so you don't have this process of signal aliasing happening, where maybe the dominant frequency isn't really the dominant frequency. Maybe it's something that's either lower or higher on this end, right? So that's really, really, really important, and it's something that we have to kind of figure out. Now, we can also proceed, once we have our harmonic coefficients, if we want to approximate essentially our signal, we can just run just like we did last time, and we see we have a pretty nice fit. Now, again, more data, number of harmonics increases, the fit gets better. Lower harmonics, worse it looks. You get the picture. Now, this signal is periodic. So you can and you should basically just cut it off after the first period. So that's essentially what we're doing in here. So if you have a periodic signal in your discrete Fourier transform, cut it off, only analyze that portion, and then you can kind of proceed essentially with your analysis, but only on that particular portion. So this is good for best practice in order to make sure that you are doing, and you can recognize that signal is periodic. And we see here that our dominant frequency could be the 0th order harmonic, or the largest non-zeroth is essentially here. So fantastic. And that's essentially, and again, you can do the same thing with, once we define here, our delta f. Delta f is this. Ooh, let's go ahead and go back. We need to define our delta, our t here. Actually, maybe, I think this is what we need to do here. It looks a little different. we still got the same rough idea. And then we can look at our approximation here. Oops. It's still reading that old delta F. Let's see here. I think we're just having an error in the code here. We have... Oh, this is that. That's why. So we need period, r dat, t dat. Oh, it should be like this. Let's double check. And redefine that here, and then let me define that here, and we can define this here. I think that we have a little bit of an issue, but I think it's just a scaling one. N from 1 to length of A of n, B of n. I think we just have this is a sign issue, but basically it will look like this. And it's just, we're just running it here. But that's just dealing with if you have a signal that happens to be periodic. So remember, and this is really, really important, when you're doing a discrete Fourier transform, estimate the highest frequency in your signal. Make sure that f of s is at least twice as large as that frequency in order to make accurate Fourier or discrete Fourier transform analysis. Use a low-pass filter to block frequencies greater than the Nyquist frequency, so that those basically won't be aliased into your analysis. So that's really, really, really important. Additionally, estimate the frequency resolution you need to make sure you don't have any signal aliasing. So essentially this. And that's it. So there'll be lots of kind of design problems associated with this. And it's going to be, actually, here, I'm going to put my curl here for just a second. It's going to be a pretty fun type of analysis in order to run these. And remember, yeah, and that's really the key. Your selection of f sub s, your selection of capital N is really, really important. When in doubt, I mean, you just have to try to max out effectively your DAC capabilities. But that should be kind of a last resort. You have to report essentially those measurements on your data acquisition device or your basically like your experimental parameters when you're calculating that data, at least to give people information and the knowledge that, well, okay, there might be, if there's an estimate or they think that there's going to be other frequencies in that signal that maybe you unintentionally aliased, that they know that when they're analyzing that data. So let me see. I'm going to stop this for a second in the video, and then I'll come back once Mathematica responds. All right, everyone, Mathematica is up and running again. Apologies for the delay. One quick note. I just want to make sure that this is very clear. Because we're doing a discrete data set instead of continuous, there should be no zeroth order kind of harmonic in essentially that loop. So we should always be going from basically n from 1 to n. So we can actually see that here. So, or essentially our R, effectively, which is what we're doing here. So that order of the harmonic. So that's a really, really critical behavior. So you can kind of see that essentially in here, your data set is going from this I from 1 to length of n, and then your number of harmonics here is going from, well, you can still go from 0 to 1, but it's going to be a little bit nicer if you can kind of just take care of this, because our data set or our Fourier approximation actually comes out the same either way here. So we can actually look at this. And then we're looking at n from 1 to length of n, and then this takes care of that a zeroth order harmonic, right? Because that's just the same thing we're seeing here. And so that was kind of why the error was giving us that issue last time, is because when we're looking at this code, we didn't have that second one, and I was still doing that zeroth order. So actually we can kind of see that. We can pop it into here, 1 and 1. And basically now we can confirm here and here. And then now we should hopefully be fine. And there you go. So we'll see you in the next video. Thanks.